For this section, there are going to be several identities that you will need to be aware of as far as double and half angle identities are concerned. All of the double angle identities are derived from the sum formulas. Double angles are defined as 2 times an angle and can easily come from the sum formulas by expressing 2 theta as simply theta plus theta. With that in mind, if we apply this to the sine, we would have the sine of theta times the cosine of theta plus the sine of theta times the cosine of theta, giving us 2 times the sine of theta times the cosine of theta. For the cosine of a double angle, there are 3 identities to know. The first of which comes directly from the cosine of a sum formula. It is the cosine squared of theta minus the sine squared of theta. However, Pythagorean identities can be applied to the squares that are present within this identity and can be simplified in a number of different ways. One of them would be to turn the sine squared of theta into 1 minus the cosine squared of theta. The other would be to turn the cosine squared of theta into 1 minus the sine squared of theta. That is where these 2 formulas come from. So the cosine of the double angle can also be expressed as 2 times the cosine squared of theta minus 1 and 1 minus 2 times the sine squared of theta. For the tangent of a double angle, the tangent of a double angle identity comes from the tangent of a sum, just as the others did. That'll be tangent of theta plus tangent of theta divided by 1 minus tangent of theta times tangent of theta, giving us 2 times the tangent of theta all over 1 minus the tangent squared of theta. Now, all of our half-angle identities actually come from these 2 versions of the double angle identity and are created by solving for either the cosine squared of theta or the sine squared of theta. So all 3 of these would be known as the double angle identities. In this and this, if I solve for the cosine squared of theta and the sine squared of theta, I would get the following. The cosine squared of theta is equal to half of 1 plus the cosine of 2 theta. That's if I were to solve this equation for the cosine squared of theta. If I solve this equation for the sine squared of theta, I would get that the sine squared of theta is equal to half of 1 minus the cosine of the double angle. These 2 identities show up very frequently in Calc 2 and in Calc 3. These are known as the power reducing identities. So called because we start with something that is squared and we end with something that is not squared. Now, solving for the sine of theta in the first one and replacing the theta with half of an angle, we'll call it alpha over 2. We would get the following. The sine of alpha over 2 is equal to, take the square root of both sides, plus or minus the square root of, we'll also condense this to one single fraction, 1 minus the cosine of alpha all over 2. The plus or minus is determined by the angle of alpha over 2. We'll go on to explain what that means in a couple of example problems. If I were to take this equation, make the same substitution and solve for the cosine, I would have that the cosine of alpha over 2 is equal to plus or minus the square root of, this would be 1 plus the cosine of alpha all over 2. Same thing goes for this as what went for this. Finally, the tangent of alpha over 2 is rather easy to obtain by taking the sine formula and dividing by the cosine formula. This will be plus or minus the square root of 1 minus the cosine of alpha over 1 plus the cosine of alpha. However, if you rationalize the denominator or rationalize the numerator by multiplying by the conjugate of either the numerator or denominator, there are two alternative formulas for the tangent of a half angle. Now, the plus or minus goes away because the quadrants happen to work out beautifully. I would recommend getting to know these last two rather than this form. These two, though, will have to be done in that fashion. These are known as the half angle identities. We're going to be making use of all of these.